Good evening, everyone. My name is Vahid Mutawalli. I'm Associate Dean for Research and Innovation, College of Engineering, and welcome you to our last in the series of research seminars given by our new faculty. So today, it's my pleasure to introduce Dr. Charles Van Neste, an assistant professor in electrical and computer engineering. He started this August as assistant professor. So he's new in this position, but he's not really new to Tennessee Tech. In fact, he obtained his Ph.D. from Tennessee Tech in 2009 under the guidance of Dr. Satish Mahajan. He then went on to become a postdoctoral fellow at the Oak Ridge National Lab, which most of you know, is mere 75 miles or so to east of us. And after doing 2 years of postdoc fellowship at ORNL, he accepted a position at the University of Alberta in Edmonton, Canada. And there he continued his research and energy research and in Department of Chemical and Materials Engineering. He has some patents already, and he had some that he developed in Canada, a new form of unipolar capacitive power transfer. And he's currently continuing that research over a broad range of areas and applications. He is a senior member of IEEE, and he holds 12 patents, with 4 patents pending, a large number of journal publications, conference proceedings, and 1 book chapter. His primary research interests involve alternative forms of energy generation and transmission, with a major focus in wireless and quasi wireless power transfer. And some of those applications are really interesting, and I've seen a number of those demonstrations in the near past. Before his current position, of course, he served as a research assistant professor in our Center for Energy Systems Research for, I believe, the 3 years prior to that. So with that, I'm going to turn it over to Dr. Van Neste, and we'll look forward to his presentation on this exciting wireless power transfer area. Dr. Van Neste.
Thank you, everybody, for coming. I guess some of you have probably seen some of this. I'm going to try to give everyone kind of an update on some of the research that I've been doing here lately. So basically, this talk will focus on sending power over and through surfaces and the various different types of surfaces and those applications. I like to start out by these quotes. Imagination is more important than knowledge. I think that's not to say that knowledge isn't important, but I think having the knowledge and then having the imagination coupled with the knowledge helps us to develop new things. And of course, as Richard Feynman would say, if you can imagine it, you can make it. And I very much believe that. So why wireless power transfer? Well, other than it being really awesome, it can increase the convenience and reduces wear of certain devices. Okay, so if you don't have to plug things in all the time, I know like with your cell phone, the plug charge always breaks. I've gone through 2 of them. Of course, I do have small kids, so that's probably a factor as well. But it definitely can reduce the wear. For EV markets, it can actually improve range, and that's something that's been very, very important to the EV market, and that's why there's a big push right now in DOE and all globally actually too, to try to develop EV charging that has wireless capability. And then of course, I believe that there are certain technologies that when applied could be potentially disruptive. And hopefully I might, in this talk, I'll show you guys one of those. Let's see here. Why is it not? Okay, it's a little bit slow. several different forms of wireless power transfer. There's acoustic, near field, far field, and EM harvesting is classified as a wireless power technology. I'll be focusing in this talk under near field, which is effectively non-radiating waves, okay? Now, what does that mean? Well, these are Maxwell's equations. You can use them to derive wave equations. And the complex power that you would get from that, this is just kind of generalized. Effectively, you can have waves that are radiating, meaning that they have active power flow leaving the antenna structure. And then we can have non-radiating, which you don't really see very often. And with this, you effectively have energy that goes out but comes back in, okay? And so that leads you to this concept of you have an antenna and the power just kind of resides, the energy resides around that antenna structure. So you would call, in a regular, like ham radio guys would say that a non-radiating antenna is a very poor lossy antenna because it doesn't produce any signals at a distance, okay? But what I try to do is use this, and what like near field is doing is using those fields that are bound to the system to actually couple to and deliver power. There's a bit of a delay here. So a very classic kind of most commercially available, most common is this idea of inductive power transfer, where you have a magnetic field, you have a receiver that then couples this magnetic field from the transmitter, and you can power devices, okay? And you can buy this. This is in your phone. Guys at MIT made this very popular. It's, you know, very efficient. You can do high power with it, but it's confined to a very small area. Okay, and that's one of the, I guess, disadvantages that this technology has. It's difficult to power things over a very big, broad area. So here's another system, capacitive power transfer. This uses the electric field coupling. Okay, and this is a bit more researchy. There's been some papers. It hasn't really been implemented commercially yet. But what you can see here is we have two plates. This is known as a bipolar configuration. So you have two plates, and effectively the electric field generated from this transmitter couples energy through, and you can power devices. This has been shown also up to pretty high power levels. Some of the main issues behind capacitive power transfer are the voltages of these plates, okay? And in bipolar, if you could imagine, if you put this in a road, you could potentially, under certain weather conditions or metal, you could short these things out, okay? So that's kind of why you don't really see this as much in commercially, at least yet, okay? Then there's this other subset called unipolar capacitive, which is kind of similar, but here you've effectively gotten rid of one of those bipolar plates. You're using a ground plane, and so this capacitance between here to this ground plane is very, very small. And to get around that, they typically have a very large plate. You don't really see this. There has been one commercial success. I wouldn't call it a success. There's been one commercial endeavor. It was not a success, where this was by a Murata company, and you could effectively put your phone on this charging pad. The problem is that the charging pad was at about a 500 volt to 1,000 volt potential. And so when you put your phone on that pad, the phone would go crazy. And people, if you looked at the comments, all the people were like, oh, this is terrible. What's going on with my phone? And so they pulled it from the market. You can still buy components of it, but effectively this was a no-go, okay? And again, just like the other capacitive, the high voltage is really the issues that you have with the plates. So during my endeavors and experimenting with this, I discovered that you could reduce the size of that plate with a coil. And if you drove this coil at a very specific frequency, you could get a pattern, a standing wave pattern. You could effectively use this like a very poor antenna, and you could bounce energy back and forth. And when you do that, you get well, I won't show this video, but when you do that, you effectively get this very specific pattern. And what this does is not only allow us to send power to a device like this using a very, very small resonator, okay, something that, this was a phone, this is a little video, I won't show the video, but you could effectively charge this little phone anywhere on the pad. The other thing that it does is it allows you to generate these standing wave patterns, okay? I don't know why they're not moving. They're supposed to be moving, but that's besides the point. So basically, when you have this standing wave pattern, you can create a nodal point that happens right here in this coil, okay? And so typically, you would have a power wave that transfers through and goes into the load. But here, by allowing a reflection point, we can have this energy bouncing back and forth. We can contain it, and we can lower the potential at this input of the resonator, okay? And so when we do that, it allows us to power devices. Oops, why is this? My computer, I think, is having a hard time with the recording on top of this. But effectively what you get is you get this non-uniform distribution along this resonator, okay? So this lowers the effective potential at the bottom of these resonators. And so as you can see here, if I were to draw the voltage along this resonator, you can see that the voltage on the plate ends up being at a low voltage. So we've done two things with this. We've enabled the system to have a very low potential at the surface, meaning that the surface is now safer, I should say, to touch, or at least interact with. You have one plate, so you don't have the same shorting issues that you had before. And you generally, using this resonator, we can make the resonators compact. So we kind of alleviated a lot of the problems that the unipolar capacitive power transfer had, okay? Here is a video, a very early video that kind of shows this, a table. And so you can see we have a single wire connected to this table, and we can energize the table with a fairly low voltage. And no matter where we place this, this resonator with a load, we can power the lamp. So anywhere on that table, even on the sides of the table. So not only have we improved the safety, but we've also allowed unrestricted power transfer over a very large area, where the other technologies, you had to be in a very small kind of place to do the coupling. So this opens up many different, avenues of utilization. Many different applications could benefit. Prior to doing this work, we had always done everything in the lab, so we wanted to take it outside to see if it would work outside, and it actually does. And so we started powering all kinds of stuff, from whiteboards to cabinets and all different types of surfaces. And even outside, it was able to work. So this is just a tent with an aluminum frame. You could connect a single contact to that frame, and you could energize the frame, and the frame itself was at a low enough voltage where you could interact with the frame. It also, you can have spill tests. I did actually test this and take measurements on this before I stuck my hand on it, but I tend not to use the grad students as guinea pigs most of the time. So very resistant, very robust, and definitely can still operate in a moist environment, which means we could potentially bring this outside. So this, fast forward where I'm at now, I have basically three major research thrust areas. One is in robotics, one is this concept of soil transmission, and another one is vehicle charging. Okay. I currently have three funded projects going. One is with the National Science Foundation. This is for sending power through the soil. The other one is actually with the United States Army Corps of Engineers. The funding actually went through TARDEC, which is why I have TARDEC listed. I won't get into that one. And then, of course, we have NASA, which is something that just started. And NASA is interested in the robotics applications. So if we look at that. So prior to doing all of this with loads, we wanted to understand, could you power something that could move around? And the easiest way of powering something that moves around is rig up a robot to do it, right? And so we built this little, we took a hex bug. Let me just mute that. So we took this little tiny hex bug, which was commercially available, and we put a bunch of wireless kit on top of it. And again, we have this little surface, and you can run this thing around. It has absolutely no batteries. This is completely battery free. And this robot will dance around the surface, which is pretty interesting. But when you drive it off of the surface, you'll see that it loses power. Okay, and the way that with the full bridge rectifier that it has on board, it will pick up a little bit of the energy from the plate over time, and you can get it to kind of move itself back onto the plate. But this shows that the system is as long as you're over that surface area, you can run this. Very quickly, we thought, well, you know, that's great, but could we control the robots through the surface as well? And so that was a big research endeavor. We got this, this was published in the Wireless Power Transfer Journal. And so we adapted these little robots to accept basically modulations of the power supply. We could get them to see those modulations, and we would just basically turn the power supply off for a very, very brief moment of time. And of course, there's a balance here. If you turn it off too much, then they'll lose power, right? So you have to kind of balance those, the communication versus sending the power. But we were able to do this, and we had 2 of these little robots that we could have dance around the surface, with their communication actually coming from the surface, which opens up a lot of really interesting possibilities, because this is all non-radiative comms. It's all done through that surface. So it's effectively like a wired communication system. And in the course of that, we started thinking, could you actually develop a robot where the robot itself is built using this wireless concept? And so what's interesting about the whole, you know, I call it quasi-wireless capacitive, but what's interesting about quasi-wireless, it's quasi because it can act like a wired system or a single wire system, or it can act like a truly wireless system. So it allows you to effectively send power through surfaces. And so if you had a robotic arm, and that robotic arm was conductive, you could effectively send the power over the chassis, okay? And potentially even the communications over the chassis. And so this was kind of a dream that I had. And then after coming here to Tech, I was able to find Michael Coltis, who was really interested in this thing, and I begged him, pleaded him to stay and get his master's degree, and he obliged. And so this became his area of research. And so this kind of shows a fundamental operation. We have a power supply, and we're effectively allowing this resonator here to act as kind of the return path. And so the charges will flow up into this, and then it stores, and then this discharges, and it comes back through the load back to the supply. So this is a single wire without a return conductor. And so this is a very, very, very early prototype that shows a regulator. Here's the resonator. And so we're effectively being able to power all that little motor from a single wire without a return conductor. And so it's got some beefy juice to it. So Michael took that and he kind of ran with it, and he developed, he put encoders on the motor, and he developed a control scheme for it. And so this is kind of the same thing. Of course, the power's not running through the chassis just yet, but it shows this concept of a single wire with the control system so that he can actually address and tell that arm where to move. And this is one of the early developments. Here's another video that shows that the same principle can work through conductive objects. Okay, and so the prior work that we had done had showed that the efficiency remains quite high as long as you're over that surface. It only drops off when you leave the surface. So as long as you're over that surface, you can have a fairly high efficiency transfer. And so this is his system running through just some random metal object that was made of steel just magnetically sticks. Okay, and so this is one of he was working with his code here. So again, a very, very early prototype. This kind of talks about the communication. I won't go too much into it, but basically you're trying to modulate the power supply in a very short period of time. If you go too short, you'll actually miss a bit. And so you have a little circuit here. And so an RC filter, when it degrades, when you turn the power supply off, that filter drops to 0. And so you can get a monostable to trigger. And so with this little pulse, you can then trigger them, like say a monostable. This is what we use for the robots. It doesn't have to be, that could just be a microcontroller, but basically you can make these short power pulses actually trigger and identify and then communicate with the device. So this is kind of a newer rendition. This, I forget what version of this was. I don't know if Michael's even keeping track of what version this would be, but this kind of shows a conventional system, and this is low frequency, basically DC. DC, you could potentially have like a rectified 60 hertz or something, but basically most robotic arms are run off of DC. This is the system using the high frequency source, and so you can see that we can alleviate one wire, which allows these joints to effectively be magnetic. And so this robotic arm can be disassembled and reassembled. So a future application of this would be to have a robot arm that could disassemble itself into a hand, right? Like disassemble and then reassemble into a hand, crawl around, go underneath something, reassemble into an arm, and that sort of thing. And so NASA was really, really interested in this. And once the NASA project started, Michael was moved on to that, and so he started developing this full time, basically. And so NASA is very interested in this because right now their lunar rovers do not have any way of swapping out their appendages. This system would allow them to basically have, like, you know, a drill bit, and then you would be able to very quickly and efficiently swap that out for something else, and the actuation is the same. Future versions, you could like actually transform the arm, and you could go even crazier with it. So this is really exciting. Next year, unfortunately, Michael is graduating, and he's not staying for a PhD, unfortunately. So this will be this project will be handed over to Tyler Markram. But next year, we're hopefully, assuming that NASA opens back up, we'll be testing this in their NASA facilities, and this is at the Marshall Space and Flight Center. So we'll be in Huntsville, Alabama. So that'll be fun. Now I'm going to shift gears a little bit and talk about the NSF project that we have. This is kind of, to lay this, I have to talk a little bit about what I did in Alberta, okay? And before I talk about that, I have to talk about this gentleman here, which hopefully everybody knows. This is Nikola Tesla. And a long time ago, and not a galaxy far, far away, Tesla spoke of this concept of being able to send power through the soil, and it was extremely cryptic, and everyone has tried to reproduce these results, or what Tesla claimed, based on his patents, and no one for the last 117 years has been able to reproduce this. And this is something that I've always been really interested in. Is this even possible? And so after doing a lot of thinking and finding some older literature that was not Tesla related, we kind of came up with this concept, so we tested it. I won't get into the details of how we had to find the place to test it, but we did end up testing it while I was in Alberta before the winter, which is important in Alberta. And so what we were able to show is that under at least a very, very, very limited less than 5 meters, like 1.5 meter radius, you could, or 2.5 meter radius, you could effectively power a small set of LEDs around this buried electrode, okay? And so I'll go into a little bit more detail. But this is very similar to what Tesla showed 117 years ago. He gave no distances or anything. He said, this is a coil plugged into the ground out in the middle of a field. That's the most detail that he ever gave for that. So did he mean actual soil ground, or did he mean like an electrical conductor ground? We don't know. We don't know how far. So in this experiment, this is the soil, and it is within a 2.5 meter radius. So when I got here, I tried diligently to try to find funding for this because I thought it would be really cool, and I knew that we could get it to go further. And so luckily I was able to get an eager project through the NSF that gave me, basically it's 2 years, gave me a funding to set this infrastructure up and start testing this. And so this is the award number, and this is effectively what we're trying to do. We're trying to generate these surface waves, propagate them out over the surface, and then be able to power these devices that are implanted in this field. And the application here is agriculture, trying to look at the health of the soil, right? Right now, it's very, very difficult to do this because each sensor has to have a battery. And you know, you could use solar and wind and these sort of things, but in an agriculture field, that just gets in the way. And, you know, as the plants grow, it's going to shade out any kind of solar you have. Equipment has to navigate around solar, solar, and it would have to navigate around wind. So really, there's no good way of instrumenting a field with lots of sensors other than batteries. And who wants to go change, you know, 200 sensors? Who wants to change those batteries, you know? So this was kind of the thrust that we went to. And so what we ended up doing is we built a Berry transmitter. And so we had found that going vertical with this, like basically having an electrode at the surface and then you bury and you put electrodes below the surface, we create a vertical geometry, which is actually not very well studied. And because of that, there's certain properties and there's certain ways when the current, when you inject currents into these, that the electric fields line up. I'll show that in the next slide. But for now, we basically had these 5 contacts. We had wires that came, each contact had a wire that came up to the surface. The reason we went through this complexity is I wanted to see how depth varied the transmitter. Like, would there be an optimum depth, right? The original idea was to keep the hole completely open and we plunge something down into it. And then we realized very quickly that the state of Tennessee actually has laws against leaving giant 500-foot holes open to the ambient. It creates ground contamination from the surface. So they force you to seal such holes. And so because of that, we ended up putting bentonite, and I went with this discrete contacts in the ground. And so my graduate student, Charles Robinson, who is also graduating this semester, this was the work that he did. And so he took a bunch of impedance, because one of the first things you do is you have this stuff in the ground, and we have to see what it electrically looks like. And so he would do a frequency sweep. And so he would get impedance of this transmitter, and this is the transmitter and the soil around it. And he would sweep through and he would basically see what the resistance was. And he took a lot of data. What we found, basically, he took like a 4-month, he did this for 4 months actually, and collected data over varying times and weathers and that sort of thing. And what we find is anything from about, I'd say 30 kilohertz and below is actually quite stable. And when you look at this data versus data that I had in Alberta, it actually corresponds quite similarly to this transmitter. So from 30 kilohertz below with this vertical electrode, you don't really see much fluctuation when it comes to weather and location, at least in these kind of conductive soil types, very much difference in that. Everything up here, this stuff varies quite a bit. Okay, and what we found too is that when you inject current into it, these frequencies actually get attenuated quite quickly, and so you don't really get the same energy distribution. So we did a whole bunch of tests. This is kind of the setup. This is sort of what we're doing. We inject pulses. Well, that's not sort of, this is what we're doing. We inject pulses. We have our surface electrode, our bottom electrode. We inject a pulse. We initially started with sinusoidal waves, but that burned up a lot of energy, so we went to pulses. And so we do these pulses, and as the pulses propagate, they produce a potential difference over the surface, and they also produce a potential difference vertically within the surface. And this allows us to effectively bury our receivers in the ground. And so this is what we have. The power source to this is a solar trailer. And so everything is off-grid, collected and put into the transmitter. Transmitter just looks like a bit of plastic pipe with some wire that sticks out. So pretty, you know, not that ugly looking, fairly aesthetic, I would say. This is the inverter, the power electronic inverter that we built to make these pulses. And this is, Brandon Neiman started working with this. And so this is a humidity sensor and a temperature sensor and a moisture sensor, all three sensors with an Arduino, a little bit of a rectification. And this is actually powered over the radius of this so that we can actually power these things and collect soil moisture data with it. So that's really exciting. In the process of using these pulses, we discovered that pulses, if you look at this, we discovered that pulses actually propagate much further for the same current and voltage ratings as a 60 hertz continuous waveform. And this was actually quite intriguing to us. And it's something that I want to look into more, and this was actually a patent that we have since published, because I have a theory. Haven't proved it yet, but I have a theory as to why this is happening. And so basically, we were able to take this up to about 15 amps. This 15 amps was using a pretty archaic system. But what you can see here is that the voltages are quite large, out to quite a vast distance. And then it drops out. And so the signal itself, we're able to see up to 250 meters, okay? And so this early on, back in Alberta, we did some scaling ratios here, and this kind of shows how the signal should, this is an exponent or logarithmic scale, but basically they look like this. And it kind of follows this trend, except for when you use pulses, you don't need nearly as much of these voltages. It actually propagates much further than what you would expect. And so that is really fascinating because it kind of shows this nonlinearity to these pulses. And as the pulse amplitude gets larger, they propagate further. And so we've done some preliminary studies looking at the speed of these pulses. And what we're finding is the speed may, and we have to do more research on this, but the speed may actually be changing. And with that change being dependent on its amplitude. And so that opens up a whole new plethora of wave phenomena. And so there are a few waves that do this. One of the kind of waves that I theorize we are generating, and I don't think we've generated a full soliton wave yet, but I think that we're on the cusps of being able to do this. And so a soliton is a form of nonlinear wave where you have a dispersion property. Basically, you know, all the frequency components, each frequency component of the pulse is trying to travel at a different speed over the soil, so it tries to spread out. But a nonlinearity in that system counteracts that dispersion and brings the system back up. So you get a pulse that propagates across the medium. Now, this is the differential equation for it. It has a solution, and so you can see here that the amplitude is actually dependent on the speed. And so what's really fascinating about these waves is they're nonlinear, meaning they don't superimpose. They actually have a nonlinear mixing. They act, when they collide, they act like a mixer. They mix themselves, and then when they break apart, they go back to their original shapes. You can see this in these different schematics. You can see how it's not superimposing. It's actually doing something a little bit differently. Our pulse generator that we have, this is basically the current pulse coming from our system. And then this is the ideal soliton waveform. So you can see we're actually pretty close. And in order to generate these systems or these waves in a specific transmission line, the pulse intensity and the pulse width are very important. If your pulse intensity is not high enough, you won't generate them. Or you'll kind of generate them, but it won't be like a full soliton. And then of course the pulse width. If the pulse width is too wide, you won't generate them either. And so they have a certain set. This is most similar to what do you call these, vortice or smoke rings. That's kind of like a mechanical analogy is to a soliton wave are these. And so you can see these two waves, when they collide with each other, they don't superimpose and pass through like a normal wave. They actually collide and extinguish themselves. Okay, so that's displaying some of that nonlinear effect. So the question is, this has never been seen before on the Earth. How does the Earth support that? And so if you look at how you can generate solitons in an electrical system, this is a standard transmission line, and you effectively just replace the capacitors with what's called a varicap or a varactor, which is just a capacitor that when you apply voltage to it, the plates would actually change. So your capacitance changes as a function of voltage. So that induces that nonlinearity in the system. So the question is, where is that happening in the Earth if we can actually generate, or we're starting to generate these waves? And so my crazy theory here is that it's actually coming from our atmosphere. So if you look at the Earth, where we're at is actually quite, the soil, or at least the surface of the Earth is quite conductive at low frequencies. And we know this because we ground all of our power distribution lines to the Earth. And lightning strikes the Earth, right? So it's definitely a low potential. It's effectively a conductive surface. The atmosphere, though, is a plasma, and it ranges for various heights. And so what you find is that these two bodies are charged, for one. The atmosphere is charged to about depending on who you look at, anywhere from 1 to 4 megavolts. And on a clear day like what we had today, we have about 100 volts per meter going up in the atmosphere. And so we have an electric field, we have two charged plates, so that forms a capacitance. But with the top plate being a plasma, if you could produce a voltage either at the surface or between these two, you could potentially cause that plasma to change, either expand outward or come down, which would change the capacitance. So with a high enough pulse, that gives us that means that we can make this Earth ionosphere cavity look more like a nonlinear transmission line, which means we just have to come up with the right pulse intensity and pulse width. And if you can do that, you can propagate a wave anywhere you want over the globe. Or at least you could send the energy where you want it to go. So the big question is, well, how is the transmitter that's buried in the Earth connected to the atmosphere? Because obviously it doesn't look like it's connected at all, right? Well, what's very interesting is when we started doing this, we saw this anomalous signal that was actually quite large coming out of the transmitter just naturally. So our transmitter in this case is acting like a receiver, and it's receiving these strange signals coming out of the ground. Now, obviously, the strongest of these signals are man-made. This is 60 hertz, 180 is a third harmonic of a three-phase power line. So there's definitely a man-made component. But then we have all of these others, 33 hertz, and what you find is that this frequency, and there's a few other subsets of these frequencies, those are actually natural frequencies. And those are frequencies that come from the Earth atmosphere cavity. We call them Schumann resonances. So the Earth has its own natural electrical vibration. 33 hertz is one of the harmonics. The fundamental is anywhere from about 6 hertz to about 8 hertz. It kind of fluctuates. But that's the fundamental of the Earth's resonant frequency. So this data shows that we actually have somewhat of a coupling to the transmitter. And that at least some of what we're seeing is natural. So the surface is actually coupled to the atmosphere through capacitance. And that's effectively what we're seeing here. This signal is strong enough where we've been able to power multiple, this is about 8 LEDs. And we've done a little bit of test. There's more to be done on this because what we found is that we can, we put in 2 more wells. And so our active thrust is going to be seeing if we can take this and actually turn it into an energy harvester. slash recapture. So we can capture the natural, but we can also recapture this waste that the power grid injects. Obviously, I was curious, and I wanted to see if this, if this is just an artifact of us being close, half a mile away from one of the Upper Cumberland's, what do you call it, distribution or substation. So I have a well at my house. I live about 7.26 to be exact miles away from the agriculture campus there. And I have a well. My well has a submersible pump. It's 500 feet deep. And I can use the chassis of that pump as a electrode. And so I can use the casing at the top as the counter electrode, the surface electrode. And so looking at this, I did an experiment. And because I'm a lot more remote, look at all of these frequencies that I saw. And so 6 hertz, that's the fundamental. I'm actually seeing the fundamental, or what appears to be the fundamental of the Earth coming from this vertical electrode. And you see all of these. And what you find out is that 60 hertz that our power grid operates at is actually also a harmonic of that Schumann resonance. So there's some really interesting things here. And I haven't been able to find any literature other than literature that says that vertical wells produce lots of noise at low frequencies. Well, I think this is the noise it's talking about. And what this means is we may be able to turn this into some sort of energy harvesting device / recapture. So the people who put this well in, they do geothermal well. They drill geothermal holes, and they typically will put over 250 of them. Well, if we're getting about 1.2 volt RMS, and you have 250 of these, you have close to 500 volts, right? On a good day, it can be as high as 4 volt RMS. So you're getting anywhere from 500 to nearly 1,000 volts if you had 250 of these with these wells all series together. So that's actually pretty exciting. And of course, even at my house, I had enough to light up a little bit of an LED, but not nearly as strong. So how am I on time? Okay, I've got a few minutes. So basically, we've monitored the power grid. We got some data from Upper Cumberland, and we compared the two. And there is some things that seem like they go together, and then there's also parts that deviate. So we're still unsure if what we're seeing is fully just coming from the substation or not. Yeah, we won't go there. This is kind of the inverter topology that we're using currently in the system. Basically, we just switch capacitors and we charge them in parallel, switch them in series, then put them back into parallel. We can do it electronically, so that generates nice pulses when we do that. We've tested some communication aspects with this. This would be like a receiver placed out in the dirt. Can the receiver use the same inverter technology to transmit signals back through the soil so that you don't have communication above ground? It all happens underneath the ground. And so it seems like this may be possible to do. And so our idea now is that you would have power pulses going out, and then the sensors would communicate in this off period back to the transmitter. So you would end up in the off time, your transmitter would end up acting like an antenna, and it would receive communication signals coming to it. Now I'm going to talk a little bit about our electric vehicle thrust. I guess I'll show it. So this was just basically going back and showing the technology we had before, where we have a surface and we can drive over that surface and we can transmit power to a device. So I'll skip this part. So well, I skipped too far. Basically, it charges up. All right, I give up. Oh yeah, here we go. So when it drives over, you can deliver, a decent, this is just the standard charging rate for those batteries, so we don't stress them, but you can charge a couple amps. And so the idea here is your mobility scooter can be charged all the time. This is the system that I built here at Tech. We're currently changing out this transmitter here because we came up with a better design. In the process of skip, well, okay. So we tried different transmitter designs. This is another one that we did where we're able to power this load pretty much anywhere over this, and over a pretty wide gap too. So we started with that aspect. Could we design these systems to be better for vehicles? And in that process, what we came up to is this geometry, which uses far less coils than the one you saw previously, but allows us to power things over a substantial gap here. So this is, there's the load. This is, I forget what it is. It's like, maybe like, oh, I don't even know. It's like 2 feet. So what is that in meters? It's like, I don't know, like 1 point, or no, point, maybe like 0.3. Yeah, something like that. So anyway, it's a pretty substantial gap. Then we can transfer energy over it. And so this is work that Tanner Minjin is doing, my other graduate student. And so what he does here is he tests various objects, plastics, he pours water on the surface. And so you see that the water itself doesn't interfere, but when he sticks his hand in between it, it changes. And that's actually really important because the system turns itself off if a large enough conductive object comes in between it, which is perfect for safety. This thing has a built-in safety feature, which is absolutely great. That's just cardboard. We'll stop there. So this is really exciting. This system also allows us to use the transmitter or the receiver as a transmitter. So these are actually transceivers. They can be both, right? So you can send power from this source to the vehicle. The vehicle could send that power back to this. So you can go both ways with it. Oh, it's also directional, as you can see here. The electric field effectively points up and the receiver points down. So you can confine the electric field just between them, which is also a very nice feature. We've done some research on this in regards to electric fields in concrete. Just if we were to embed this in concrete, would the concrete destabilize over time? And I had 2 very bright civil engineers working on this, Macy Arms and Kayla Truman. And they actually built the concrete block. They developed a little sensor so that they could test the speed and the modulus changes if there were any. And they, of course, used a FLIR, which is an IR camera, to basically look at the thermal heating of this. And so you can see the nonlinearity of the transmitters as it's being powered, and the heat coming from it, which is a very small thermal gradient, I should add. So it didn't really do much damage to the concrete, which is a good thing. Lastly, I just want to point out that these quarter wave resonators, you can do all kinds of really fun things. Dr. Langiri in the mechanical engineering, I've been working with him to develop this concept of water heating. And this actually came out of my work in Alberta, where we were trying to figure out ways of treating tailings water, which I won't go into it, but they do a lot of surface mining of bitumen, which is like oil. And so this is kind of the sludge that comes out of that. We found electric fields could help separate that. We also found that you could RF heat the water. And so this is a little, there we go. that was a little water rocket. So we basically boiled the water inside of it and was sealed. And when the pressure got high enough, it shot itself off. So there's a lot of applications you could do with that. And the last slide to show, this is something that I haven't really done while I've been here. It is on the horizon and I would be interested in pursuing it, but it's this concept of wearable. And in fact, this technology allows you to charge up in a very safe manner your body. And so this is a little inverter that I strapped, and I can charge myself up and use my body surface as kind of like the table surface or the earth surface as you saw on the other slides. And so I can power things anywhere over me. And so this would be really cool if you had like a little sensor that, you know, could monitor your blood pressure or your oxygen, your oxygen level, something like that. And so, yeah, this would be a really neat kind of biomedical application. And so if there's any students out there interested, let me know, because this could be something we could play with. And with that, I will conclude my talk.
Excellent. Thank you so much. That was fascinating as usual. So we have a few minutes for questions and answers. And so anyone that wants to ask a question, please just unmute and show your video. We like to interact a little bit more while you're having questions. All right, Dr. Sagolzai.
Hi, I have a quick question. It was a great presentation. Thank you. So when you mentioned controlling those robots through wireless power, what's the frequency of transmission of information? Let's say if you want to send some of the sensory information and you want to send some control actuations, so how fast it can be transmitted over wireless power?
It needs to be slower than the resonator. So the resonator, I think in that instance, the data transfer rate was like 44 kilohertz, so very, very low for driving the robots. You could potentially bring it up to maybe potentially a megahertz. It really depends on the resonator. If your resonator is a high enough frequency, then you can actually get it. So if it's like a 10 megahertz resonator, then you could potentially do maybe a 1 megahertz comm signal. If it was a 20 megahertz resonator, then you could go up from there. Okay, but your limitation is actually the resonator and the ring down time, the quality factor of that resonator.
Yeah, that's great. Thanks.
Yeah.
What is the upper and lower limit of power transfer that you can have in some of these typical systems?
What we've tested so far is about 100 watts. I believe that you could go significantly higher than that. The limitations right now are really on the switching power electronics aspect of it. You can go as low as you want. Going low is never a problem. So, but it's going higher that ends up being quite the. You get to a point where you're better off just using like a vacuum tube triode type thing. So that's kind of where you end up going if you go high enough powers. So.
We have quite a few audience, so there's a question or two that are brewing in there. Right?
I see a lot of students from my field class. Now's their time to ask me the hard questions. I'm usually asking them the hard questions.
Right. So I didn't quite, I mean, being a mechanical engineer, you can't blame me, but I didn't quite understand all that you were discussing regarding the use of the atmosphere and earth and so on in terms of power transfer and the dipole, I guess, that you create. But do you have to, what you were describing, do you need an infrastructure for it, or is it, how would you achieve it, right?
So far right now, we're using a buried electrode system. So you would have to have a buried electrode system. The efficiency comes with how well you can make the contact, how low that resistance is of the transmitter, because the propagation that we see is based on current. So the idea is you want to make it as low as possible so you can put as much current in as you can at the lowest voltage possible. And then you have to do a pulse. And so as that current impulse gets larger and larger, over a larger area too, you can induce these effects in the ground, which ripple into the atmosphere. That's my theory. I don't know. That I could be completely wrong. I'll find out, hopefully. So, it's kind of like a, mechanically, I guess if you want to think about it, have you ever seen how they make a vortex ring from a box? They take a cardboard box and they drill a hole. Well, if you take the box and you slowly move it back and forth, all you would do is push air in and out of the box, right? You'd have no vortices. If you start to impulse it a little bit, right, you'll start to produce kind of a partial vortice, but it won't really propagate very far. And I think that's what we're doing now, electrically. If you give it the right amplitude and the right pulse width, because that's important as well, then you can shoot the vortice across the room. Okay, and so that's where I want to get to. I want to figure out what that impulse needs to be. My guess kind of says that it may have to be almost like a lightning type pulse, but I don't know if it really needs to be a current density or I suspect it needs to be like a current type density pulse that you would see from lightning. Okay, but that would of course be to ripple all the way around the globe. Most of the times we don't want to do that. We want to be able to send and direct it in locations where we want it to go. So
it is definitely fascinating. Any other questions? None of the students want to challenge their professor. Okay.
It's being recorded, I think, then.
Well, we can always stop the recording, and then after that, they can freely ask questions.
I've just been challenging him the whole way through my thesis, so I don't think any questions I've asked would be valid at this point.
All right, with that note of giving up on asking tough questions, we will thank Dr. Van Neste for a very interesting presentation. So I thank everybody for attending and wish you a very pleasant evening. And yes, may the electrons be with you.